Imagine you're stirring a pot of paint, except the paint is actually a magnetic field. Now, if you stir just right, you can make tiny patterns explode into something huge. In nature, that's the dynamo idea, how the sun or earth could keep a magnetic field alive. Here's the shocking twist. The researchers build a divergence-free velocity field on the 3D torus, T3, by drawing random variables independently, on short time blocks. Think of it like switching the fan direction every few moments, but with one rule. The flow stays incompressible. No squeezing, no leaks. Then the magnetic field evolves by the resistive induction equation. Resistivity here is a knob K. And the big question is, does the magnetic field still grow fast, even when the resistivity is small? Their result says yes, almost surely. For every sufficiently small fixed K, the exponential growth rate is at least 1/21/2, a concrete fast dynamo lower bound. That's not just growth happens, its growth happens at a provable minimum speed. Now picture the magnetic field as a choir of Fourier modes, each singing at its own frequency. In most dynamo problems, you'd need to track the whole orchestra, infinitely many notes all at once. But this paper finds an algebraic structure in the Fourier-space of the solution operator. So instead of hurting the entire choir, the proof only follows 3 carefully chosen notes. It turns the complicated dynamics into a simple recursion, tracking how the logarithmic size of those modes evolves from one time block to the next. And there's more. They even get a time-uniform lower bound with a random prefactor that satisfies inverse moment bounds uniformly across K in a range. Translation: the how big you start randomness is nasty, but not out of control. If you love math that's both wild and rigorous, you need to watch this. Subscribe and tell me in the comments, should we try to explain fast dynamos using music next?